Hello, and welcome back to STEM Online Academy. My name is Jason Masterakos. For the subscribers out there, you already know who I am. You know what this channel is about. But for new viewers and potential subscribers, STEM Online Academy, which was created by me, is a channel that discusses advanced mathematics, physics, and engineering concepts, advanced concepts, and problem solving through a very unique lens. Okay, so let me go through what that lens is. All right, we target specifically undergraduates, graduate students, and even enthusiasts who have an interest in advanced mathematics and physics. Okay, so the way we do it, right? We're trying to motivate, um, you know, either new learners who are interested in these areas, or to enhance your problem solving or into mathematical intuition for abstract concepts. Okay, so I have a three-pillar technique that is actually pretty useful, and you should follow it yourselves, right? I always like to go through the three-pillar technique, and the technique is this. When it comes to learning anything, it's not always possible to do it. I have to admit that sometimes even I can get stuck, right, on a complicated problem. It doesn't work all the time, but it works a lot of times. Okay, and that approach is to one, make sure that whatever problem you're doing, whether it's a word problem or an equation or it's a geometry problem, doesn't matter the area of math or science, right? Well, matters if it's in math and physics mainly, right? But it doesn't matter what subfield it is. Make sure you understand the problem semantically well. What do I mean by that? You want to make sure that you have a strong foundation in what is being understood. Okay, maybe reread the question, right? If you don't understand it the first time, maybe try and create pictures in your head of the words. So take the words, right? Let's say if it's a word problem, and try to picture what you're reading in terms of the problem. Try and translate the words into pictures in your mind, and then from there, take it from there and try to make sense out of it mathematically. That usually helps when it comes to reading problems. Okay, reading and understanding problems. So that's step number one. Step number two is always make sure that you have some sort of model, right? Either what I mean by a model, I mean a geometric model or a graphical model or simulation. Okay. Now, why is that important in math? Well, first off, you can't understand the problem. You can't make sense out of it unless you know how it looks like. Okay. So you want to make sure, for instance, let me give you an example. If I want to calculate the area under a parabolic curve, for instance, right? Okay, so if I want to calculate the area under this parabolic curve that I'm drawing here, okay, let me highlight this. Okay, so if we look at this region here, okay, if I want to calculate the area under this curve from let's say 0 to 1, all right, this guy here, well, first off, I better make the diagram in the first place because when we're calculating areas, we want to be able to know how to integrate correctly, and you can't integrate correctly unless you have the limits of integration, and you can't get the limits of integration correctly if you don't have a geometric model. So this is a classic example of why drawing graphs is very important, or any type of model. Okay. Now back to my point, why it's important, not just to find unknown variables for your problem, but also to see if your final result will make sense if it matches what the geometric or physical model is representing. I know this is the area under the curve, okay? if I want to calculate this area, my area better be positive. Why is that? Okay, I want you to think about that for a second. Why should my area be positive if my curve is above the boundary here? Well, the reason for that is because it's positive. Okay, the curve is above the x-axis, so in that case, the bounded region for the area under the curve has to be positive. Okay, so since my area has to be positive, when I do any type of numerical calculations, it better come out to be a positive answer. If you see a negative answer whilst you're summing up all of your rectangles, or you summing up the rectangles of your limit, which is equivalent to the integral, uh, let's say it happens to be negative, then looks like something is wrong, right? So that's two reasons why creating graphs and models is very important for uh, a math problem, not just calculus. It could be any type of math problem. Okay. Okay. So and then finally, from step two, the step three part is to make sure you translate the geometric model or graph into a mathematical equation. Okay. Now, easier said than done, and you're probably asking, how do we do that? Well, it's there's no formula for it, but the thing is, you want to be able from the model when you make your model, make sure you have your quantities on your diagram, maybe letters or whatever, and these letters and words or whatever on your diagram represent something that can be uh, translated into a mathematical expression, which you will know how to solve. How do you know how to solve it? You've learned methods in school, you learned systems in school of how to solve certain types of equations. So step three is the easiest. Step one and step two are always the most annoying. Okay? All right. So you want to understand the problem, then uh, create a model that makes graphical sense, and then from there, part three, uh, translate it into an equation that you can use a mathematical method on to solve it. Okay. All right. Now let's get back to uh, my channel, right? So if you've watched my last couple of videos, I've been going through well, in general, I don't just go through math, I go through physics problems as well, especially problems that require, you know, that are not always in curriculums, like in AP or IB classes or university classes. But trust me, those problems will be in those classes. They're just meant to help you think sort of out of the box. They can be a little tricky, but I try to compress it and make it simple using my three-pillar approach. But today, what we're going to do is we're going to continue with my book, right? And actually, the last couple of videos I've been talking about it, right? Advanced integration techniques, where we master advanced integrals, applications, and there's a section on open-ended problems as well. Okay. So in the last couple of videos, we looked at some really interesting integrals. Okay. By the way, it helps for this book if you know uh, integral calculus and linear algebra. Okay, those are the foundational staples. So if you have done, let's say grade 12 AP or IB courses, and or first year university, preferably first year university because it's more solid foundation. You should be able to understand the mathematical methods. They build up in difficulty, but they are all based up on stairs, right? One thing leads to the next, leads to the next, leads to the next. It's just getting knowledge. The hard part about this book is the applications and the open-ended problems. Okay, but if you're a person who wants to learn more about integration at a higher level, not just basic integration, uh, this is the place to be, right? Because you're going to learn about things past U substitution, trig substitution, integration by parts, and so on. Okay, will be handy in your other classes. or if you're a person who enjoys challenging problems that, and when I mean challenging problems, there's a section in this book where the problems are unsolved. So if you're one of those people who enjoys looking at stuff like that, go ahead and try it. I don't know how to do that section. I put them in the book just as a thing, see if anyone can solve it, but I've tried. I can't solve them. I may not be smart enough to solve it, but maybe someone can, and maybe in the chat someone can, you know, always say something in the chat. That would be really great. Okay, so I'd be interested if you know how to solve the uh, really challenging ones in the book. So, anyways, today we're going to look at a interesting integral called the multidimensional integral. Okay, so this is an integral. Obviously, it says I don't want to be funny about it. Well, I will be funny about it. It's a multidimensional integral, so that means that you have integral product and number of integrals. Okay, so a multidimensional integral, and specifically on a Gaussian. Okay, so let me talk about a theorem here that's very important. The theorem states, we're going to need to use this theorem, it's in my book. Let capital D be a symmetric positive definite matrix. Okay, as I said, it's really important if you have some a good strong foundation in elementary linear algebra as well. Okay, because that's what this theorem uses. So let capital D be a symmetric positive definite matrix, and let F map a region Rm to R. Okay, so R is a region. That's what R is defined as, where f of x is equal to e to the power of negative of x transpose, that means transposing the matrix, times matrix, the inverse of the matrix D times x. Then what we get into as a result is an integral of e to the minus x transpose times D inverse times x, uh, taking the differential with respect to x. That n there means that we have n number of differentials, and this should be equal to little pi to the nth power times the determinant of d all to the 1/2. Okay. All right. So we want to be able to prove something like this. Okay. So this is what we're aiming to prove. Okay. So we have to be able to do this proof. Now, the way we go about it, we want to prove this theorem. We want to prove that this theorem implies that we get this integral. Now, to start the proof, you guys may think it's, you know, step one might be a little bit of my three-pillar process solving mathematical problems, may be a bit, I don't know, not to use it all the time. Okay, sure, but here's an example of where we're actually going to use step one. We have to understand step one very well in order to solve the problem. It's a sequential approach from step one to step two to step three. Okay, right? So step one, right? Remember, make sure you understand the words. Okay, what's being asked and what is the not just what's being asked, but the implication of what is asked. Okay, so based on what we're reading here, right? We want to find, we want to have a symmetric D, a symmetric matrix that's positive definite, and so that's where it's positive definite, and F maps Rm to R, where we've already defined our function, and it results in this crazy looking integral. Okay. Now, you'll notice that this is a if P then Q statement, right? Remember, when you do a proof, that's where I get step one as being a pillar for solving mathematical problems. Everything uses, uh, even though it doesn't look like, or we don't say it in mathematics, right? Even though it doesn't look like, and we don't say it, everything is predicated on using what's the word I want to use? Every mathematical problem is predicated on using some of the basic principles of logic. Okay, if P, then Q follows. All right. So in this case, statement P would be, since D is real and symmetric positive definite matrix. Okay, that's P. Okay, so let's say this is P here. Okay, let me highlight. Okay, so this is my P statement. Okay, And then over here, this is my Q. Okay. So as you can see here, it's an P then Q statement, right? If P then Q. So we're going to do a direct proof, right? So we know P, so starting the proof, we know that since D is real and a symmetric positive definite matrix, okay, then I can say capital D inverse all transposed, okay, is equivalent to D transposed to the -1, right? Because I can interchange the transposition with the inverse of the matrix, okay? Right, so those of you in linear algebra, currently taking linear algebra, um, yeah, you should understand what I'm saying. Even if you don't follow everything that I'm saying, because some of the stuff you may not have prerequisites, I hope you'll be interested in learning more on this stuff. So D transpose inverse, and this will equal D inverse because D is real and a symmetric matrix. Okay. Another thing too I want to mention here that's very important. Okay. Look carefully at that I'm defining A equal to D inverse. Why am I doing that? I am doing that because of the notation. Okay. All right. Well, the notation would be integral e to the negative x transpose a ax dx is what we want to prove. All right. So I'm just replacing the d's with a's. It doesn't matter what I call it. I'm going to let a equal to d inverse. Okay. So where matrix A, I've written it here, is equivalent to matrix D. Always make sure you're explaining everything as much as you can. I know it's not always easy, but it just takes practice writing stuff, right? Right. So think of mathematics as taking an English writing course or a logic course. That's what mathematics is in reality. Okay, it's one or the two. Right. So where matrix A is equivalent to matrix D. Now let's now try to decompose. Now, what do I want to decompose? I want to decompose this. Okay. So this is what I will decompose. So continuing, I'm decomposing A into capital A matrix equals. I'm going to explain what all this is. You don't need to be terrified. Don't be terrified. It's not that bad. Okay? So A is equal to T, capital T times lambda times capital T inverse. Now, let me explain what the T is. T is going to be called an orthonormal matrix. Okay? So you should know what an orthonormal matrix is, right? You have some piecewise base. It's almost written like in a piecewise notation. E sub ij, E sub I times E sub I is equal to 1 if I is equal to j, right? The indexes. And E sub I times E sub j equals 0 if I cannot equal to j. So I am using the thing of orthonormal basis, right? Now, here T is an orthonormal matrix, just to clarify. It's an orthonormal matrix. And lambda, right? Lambda, capital lambda, is going to be a diagonal matrix of the eigenvalues of capital A. So it's a diagonal matrix of the eigenvalues of A. Okay. Now, given that information, how is this handy? Very straightforward. It is handy because of the following. Okay. We know that we have an integral here. So our integral e to negative x transpose ax dnx, right? Okay, so that's what we're starting off with. The original theorem said D instead, but I'm going to use A. Um, that's usually how we started with. This is the A is what we want to prove. This has to be equal to the integral of e to the negative x transpose times t lambda t inverse x dnx. All I'm doing, I'm substituting the A matrix in. Okay, I'm substituting the A matrix for it's the diagonalizable matrix, right? Those of you who have taken linear algebra or are in the process of it, you'll notice from your lecture notes, if you've taken your university classes, that this here is equivalent to A equals PDP inverse. Right? So where P is the other matrices, D is a diagonal matrix with all the eigenvalues lambda in the diagonal matrix. Okay. All right. So I hope that is making sense. I'm just trying to relate stuff to what you know based on my audience. Okay. So that's why things make more sense. And hopefully you are, for those you don't know, are more interested in learning these concepts on your own, or with my help, of course. So then we have this integral here. Now, since t has to be orthonormal, we have the fact that t inverse has to equal to t transpose. Right? That's a fact that can't be disputed actually. Right? T inverse has to equal to t transpose. There's no way around it. Okay. Now let's define a new variable. Okay, I'm going to let y be my new variable. It's going to be called t transpose x. Okay, t transpose x. Okay, so that's interesting. Now, why am I defining a new variable? It's going to make more sense. I'm just going to substitute it into my previous integral. Okay, that integral right there. And then this integral now will be e to the negative x transpose times t lambda t to the transpose x dnx, right? So I'm just replacing this with this now. Now, where does that y come in? Well, notice y is equal to t transpose x. We've defined the variable y. I'm going to substitute to the best of my ability here. Okay, so by transpose lambda y, okay, that's what it's all to, times a Jacobian, so it'd be a Jacobian differential, it looks like. Okay, so we have a Jacobian differential. Okay. How do we know this? Well, J is the determinant of the Jacobian matrix. Okay, so JMN is equal to dx subscript m with respect to dy subscript n. Right, some multivariable calculus. Well, most of this is multivariable calculus with some linear algebra. Now, since another thing I want you to notice, since lambda, capital lambda is a diagonal matrix, the integral will be separated into a product of n independent Gaussian distributions. Okay, so this is a Gaussian integral. Okay, e to the negative ax squared is always equal to root pi over a, where a is a constant in the exponent. All right. And if we go to the next page, since it's a product of Gaussian distributions, our integral can be rewritten. Integral of e to the negative y transpose lambda y dy is equal to the product. Now, for product notation, I'm defining what I have down here. Okay, I probably should have put it above, but no, it should be fine down here. I'm going to explain what this is. This capital pi notation. So capital pi, just like how we have a capital sigma notation for sum, capital pi represents n number of products, n number of times we're multiplying something from an index k equals 1 to n. Okay, so it depends how many times. It's just good if we're lazy not to write out our entire multiplication of integrals. I'm just saying capital pi. Okay, in mathematics, it helps to be lazy. Best mathematicians are lazy. Not always true, but anyways. Okay, so e to the negative lambda yi squared dy subscript k. Now, I'm going to explain where this is coming from. Since x is a row vector, x1 to xn, and dnx, right? And the differential is equal to the pi notation from I equals 1 to n of dxi, right? I'm just substituting this information here, and that's why we're getting this pi from k equals 1 to n times the square root of little pi over lambda k. All right, and you'll notice from here that we get this equal to all under the square root of pi to the n. Think of it this way. I'm taking the pi notation of little pi. That means I'm multiplying my little pi n number of times. That's equivalent to pi to the n, right? If I multiply pi times pi to the first pi square, pi 3, pi whatever, it's n number of times because our product goes from 1 to n, all divided by the capital pi product from k equals 1 to n of lambda k under the square root, right? And then from here, we're going to get this equal to the square root of pi to the n all over the determinant of capital lambda, right? Because pi of lambda k, that's just our determinant. Pi of k equals 1 to n of lambda k is just saying that I have some sort of, I'm taking the determinant of the main diagonal only, even though the terms don't work that way. But determinants of the main diagonal of a matrix, you only take the determinant of the main diagonal of the matrix if you have an upper or lower triangular matrix, or it's a mixture of both, right? So that's why there's a capital lambda there, okay? Now, since the determinant of A, which we said earlier was T lambda T inverse, right? I can split up that product. It's all under the absolute values, but I can split them up. In reality, they're not absolute values. I shouldn't say that. That's not precise. Yeah, I have to correct myself. They're not absolute values. They're determinants. So I can split up the determinant products individually. So determinant of T matrix, determinant of lambda, the lambda diagonal matrix, determinant of T inverse. And this equals lambda. T's cancel. And this means, with the information substituted above, we can see that this is equal to the square root of pi to the f power all over the determinant of A. Okay, so now we have this information. Now, from this part on, we can finally say that this implies that the integral of e to the negative x transpose ax dnx is equal to pi to the nth power times determinant of A. Okay, and we've done the problem. We've proven the problem from the book. Okay. So I hope, I know my style is comprehensive, but I hope it's the most effective way of learning this stuff. So I hope this helped you guys. For new viewers, it would be great if you can like and subscribe. Try to watch the entire video for a very comprehensive approach of how I'm doing these. For all of my videos, you're gonna have to watch the whole thing. Don't skip anything, because if you skip, you're not going to be able to digest it. Digest like the small parts, which is really important. Okay, so like and subscribe. Um, if you want to learn more about integration, you can always check out my book. It will be in the description below on the YouTube channel. I always have the link there. And there'll be plenty of more YouTube videos coming. I'm going to be on more often. Okay. All right. So don't forget, like, subscribe, and have a good day. Bye-bye.